Okay, hi everybody. So today we're going to continue on 5.3. Last time when we came to a good stopping spot, so I figured I'd make that video a little bit shorter and then we'll continue on today. But before we go ahead and get started, if you don't notice, I have different glasses on, which is actually my old pair that I had broke at the beginning of the semester because last night this happened to my new glasses. And I don't know what's going on. I was literally just taking them off my face and they broke. And I was like, what the heck? Anyways, I was so mad because these are like brand new. And I actually can see better in these because they're not so scratched up. My right lens is like so scratched up and it's hard to see. And then I really can't fix this because it's like cracked, broken. I don't know how that happened. And I'm not about to wear contacts at home. I don't like wearing contacts as is. And I did my best to like fix these, but I honestly don't think I did it right because they fit my face super loose and it's so awkward. So I'm probably gonna order some new ones, but I'm annoyed and I'm over this glasses things. I never break my glasses this much. I usually keep a pair of glasses for like 2 or 3 years. I'm coming on my 2 year mark on these. But yeah, this year has been super odd. But whatever, we'll get through it and we'll finish Calc 1 and it'll be great. So in the last video, we talked about what was called a definite integral. And so we introduced that definite integral by saying that we can find the area under the curve by using that evaluation theorem instead of doing Riemann sums over and over again. And so if you recall, this is the notes we took last time. Basically, we use this integral notation here to say that we're going to take the antiderivative. And the way that we found those definite integrals is instead of taking that Riemann sum when we write the integral from a to b, we just evaluate capital F of b minus f of a, which we evaluate those antiderivatives. And so now what we're going to talk about is some notation. And I know I had mentioned this earlier already, but what's the difference between a definite integral and an indefinite integral? So an indefinite integral actually doesn't have bounds here from a to b, but a definite integral does. And so I mentioned in the last video that when we have a definite integral, we don't actually have to put this plus c at the end because it's a definite integral. We're looking for the area under the curve between those two values. But for a definite integral, we definitely will have to do that. But I'm sorry, for the indefinite integral. So if you have an indefinite integral, to evaluate this, we just take the antiderivative and recall that we denoted the antiderivative by capital F. And so this means that if I take the derivative of my antiderivative, I should get back my original function here. But I do want to mention this note. This note is super important for you to understand that indefinite integral, right, the one that we're talking about right now, is actually a function. But the definite integral is a number. So the definite integral gives us the area under the curve, but the indefinite integral gives us a function. So recall in like 4.7, we found the antiderivative and then we got a plus e. And we ended up with the function. Sometimes we could find the c value, sometimes we couldn't find the c value. And so that's what makes the definite and the indefinite integral different, is that for the indefinite integral, we're gonna end up with a function. For the definite integral, we're gonna end up with the number, which is going to be the area under the curve. Okay, and so the relationship between the definite and the indefinite integral is that if we take the definite integral and evaluate it at some bounds, it's the same thing as a definite integral. So let's do a few examples so that you actually maybe understand this a little bit more. But for example, if I take the integral, and I'm going to do the indefinite integral, so that means my bounds are not defined, of x cubed plus 3 dx. Okay, so I know that if I want to evaluate this, I have to take that antiderivative of this function. And so I can take that antiderivative by saying, okay, I can add 1 to this here and then divide by that new number, 3 plus 1. And then here I have a constant, so I'm just going to tack on that x because we're integrating or finding the antiderivative with respect to x. So this here tells us the antiderivative with respect to x. And so to evaluate this, so as I take the antiderivative, I no longer need that integral sign, that crazy looking s. I could just write x to the 4th over 4 plus 3x plus c. And now I actually do really need this c. It's important because now I don't have bounds. I'm not evaluating it from one place. I'm not evaluating from a to b anymore. I'm just taking the overall antiderivative of this function. So I'm evaluating the integral. And I need that plus c because if I take the antiderivative, if I take the derivative of my antiderivative, my c is just a constant, so we know that it can go away, it will go away and disappear as 0, so we don't know what this is unless we have some underlying conditions like initial conditions in our velocity problem. And so this is the way that you would evaluate the indefinite integral. And so let's do one more example, just so we get this down. Let's do the integral of sine x dx. And so remember that if we're doing the integral or the indefinite integral of sine x dx, we have to kind of maybe even think backwards and say, what can I take the derivative of that will give me this sine x here? And the only thing that will get you a sine is cosine, but because when we take the derivative of cosine, it's negative sine, and here we have a positive sine, then this means that my antiderivative is going to be negative cosine x plus c. Because the antiderivative of negative cosine is negative sine, which gives me this positive sign here, which means we took the antiderivative correctly. And then we can't forget that plus c. If you forget that plus c, I'm going to take away major points on your exam. So please do not forget that plus c. Okay? And so basically, when you're learning definite integrals and indefinite integral, when you're learning your definite integrals, it's kind of the same process as when you were learning derivatives. We gave you a bunch of rules and said memorize them, and this is how you're going to take that derivative. Same thing's going to happen for finding integrals or finding antiderivatives. Is now you're going to have the backwards version of those derivative rules, and you have to know and understand them and be able to do this on the exam. And not only that, but most of you who are moving on to Calc 2, when on your first day of Calc 2, they're not going to baby you and say, oh, okay, let's relearn definite integrals. They're not going to do that. The first thing that they're going to do is they're going to just start doing antiderivatives, and you should have already known how to do these. And so now what I'm going to do is I'm going to actually give you a table of the definite integrals. I took this from the book, and I would highly suggest that you make flashcards and try to memorize them as best as you can, not just for my class for the final, but also Calc 2 class day 1. They will expect you to know this. I'm not even kidding. So let's actually go over those tables of definite integrals. Okay, so I wrote these ahead of time just so I would save time on the video and not have to write them all out over and over again, but some of these are properties and some of these are definitions, basically what you're gonna have to know. So here we've seen this one before. Some of them we've already learned before, like in 4.7 for antiderivatives. Same thing here, is that if we have a function, if we have two functions, we can separate and integrate respectively. So the sum of the integrals is the integrals of the sum. And this constant here says that we can pull out that constant, just like you were able to do with derivatives. Nothing new, nothing different. This one is the one you've always been doing. When we add 1 to each of these and then divide by that number, that's all that says. And then they give you all the other ones. Now I would highly suggest that you pause the video right now and write these down. There's actually another page after, because I write pretty big. Write them down, make some flashcards, write it on your mirror, make post-it notes around the house, and try to learn these because it's really important. Like I said, not just in my class, but in Calc 2 is super important. So an easy way to check you have the correct antiderivative is if you take the derivative of the function on the right-hand side, you'll get the function inside here. So for example, we already did this one in the last section. And for this one, we have the integral of sine squared x, and that equals tangent x plus c, which makes sense because the derivative of tangent x is secant squared x. And similarly, the derivative of secant is secant tan. And so remember, you're just going backwards here. And before, when we took the derivative of an inverse tangent, the derivative of an inverse tangent was 1 over x squared plus 1. And same thing here. And for this one's a little bit of a tricky one to kind of memorize, but I think I did go over it in 4.7 as well, is that if you have something like 1 over x, right, that power rule does not work for something that's when x is equal to -1. So what you need to do is you need to recognize that when you take the derivative of an ln function, you actually get 1 over x. These are a little bit tricky, so like I said, take the time to memorize them. You need them for Calc 2 most definitely. So now let's move on to that next page because there's a few more. So go ahead and pause this video right here, write them down, try to commit them to memory, talk to yourself, talk to your classmates via Zoom, whatever you have to do to try to memorize these, okay? And then I would highly suggest that before you start that summer or fall semester when you're about to enroll into Calc 2 is to go back and kind of review these integrals one more time because I want to make sure that you're set up nicely for Calc 2. Okay, so that when you get there, you're like, I know my antiderivatives, let's get going. So let's do a few examples on how we would use these tables of integration to evaluate indefinite integrals. And at first, when you're learning these, you'll probably going to be looking at your integration tables over here, the ones that we went over a lot because you don't have them committed to memory, and that's okay. That's pretty normal. But the more that you do them, the more comfortable you'll get with them, and the more you'll be able to see an antiderivative or see an integral and know how to integrate that integral. Just like with derivatives is now you're really comfortable, and when you were first learning derivatives, you probably had to go back and go, oh, what's the derivative of tangent again? Or what's the derivative of secant again? But now hopefully you are able to just look at the derivative of tangent and be able to do it very quickly. So same thing here. So let's do an example. Which is that if I have the integral of 10x to the 4th minus 2 secant squared x dx. Now for this, you have two choices. I have mentioned this before where you could just integrate this because that you recognize that the sum of the difference of the integrals is the sum of the integrals is the integrals of the sum and vice versa for differences. Or if you like, you can rewrite it so that you get 10x to the 4th dx minus the integral of, and then I'm going to pull out that 2 secant squared x dx because I can. Pull out a constant. That was one of our properties. So we had two properties here. Maybe I should write a plus and minus here. Is that we can break up integrations like this, and then we could also pull out constants. And now for this one, all we're going to do is we're going to do that antiderivative backwards power rule where we add 1 to our exponent and then we divide by our new exponent. So for this one, we'll get 10x to the 5th divided by 5. And I know I need to do that plus c, but because this was my entire integral here, I'm going to wait to do the plus c till the very end because there's no sense in adding a plus c here and another plus c here. Actually, let's do it just so I can show you why you don't need to do that. And then for this one over here, what we'll do is we'll do -2 because that 2 is out there. And now we're going to take the antiderivative of secant squared. And now maybe we need to look back at our table and say, okay, where's my integral of secant squared? It's not on this page. Maybe we can find it here. Oh, there it is. So the antiderivative of secant squared is tangent x. which makes sense because the derivative of tangent x is secant squared x. So this will be tan x plus, and I'll call this C1 and C2, and then I'll show you why we don't actually need to do that. So now if we simplify, this first term will just be 2x to the 5th, and then I'm going to write 2 times tangent x here. And now the reason you actually don't have to write C1 plus another C2 for these is because if I add C1 and C2 together, they're like terms because they're both constants, correct? So they're both constants, but when I add them together, I'm just going to get another constant. So I can just lump these two together and make one big C value. So you don't actually need to rewrite them over and over and over again. Okay? And now we'll do 2 more examples, and then we'll go into that net change theorem at the very end of the section. So let's do another example so that we get very used to this. And we'll do the integral of 5x minus 5 to the power of x dx. And so again, we are able to separate this like this. And hopefully now you're very comfortable with taking the antiderivative of something like this, where you just add 1 to the exponent and then divide by that. And so this one here is going to give me 5x squared over 2 minus, and I'm not going to do that plus c because I just showed you that we don't actually have to do a plus each time. We just need to do an overall plus c for this. And now the next thing we need to do is take the antiderivative of 5 to the power of x, which is the same thing as taking any constant to the antiderivative of any constant to the power of x. And so now would be a good time to actually look back at our derivative, and our integral tables or our antiderivative tables, and see which one matches that so that we can do it. And so if I look back, I actually see it right here. And so the antiderivative of a constant to an x to a power of x is going to be ax divided by the natural log of a plus some constant c. And so now if we go back, we'll get that this is actually equal to 5x divided by the natural log of 5 plus overall constant c for that integral. And so that's not that bad. So just remember the 2 differences between a definite and an indefinite integral is that for a definite integral, you have defined bounds at these spots here from a to b, right? From a to b. And for a indefinite integral, we don't have bounds to define them, so it ends up being a function. And for a definite integral, we actually just end up with a number we evaluated, okay? And so, and again, the relationship between those two is that if I have the antiderivative and I evaluate it from a to b, it's really the same thing as doing my definite integral. And so now let's do one more example and go back to our definite integral. So let's do C. Let's do 1 over 4 absolute value of x minus 3 dx. So if I stop here and I kind of look back at my integration table, I actually don't see a rule for my absolute value. So how do I integrate something with an absolute value? Well, that's an excellent question. So what you're actually going to have to do is, we know that for an absolute value, we are able to write it as a piecewise function. And so that's exactly what we're going to do. So remember that we can rewrite this, and we can rewrite it as a piecewise function, or if we look at the graph of this function, right? This is the same thing as a regular absolute value graph, but now it's been shifted over to the right 3. So normally our parent function looks like this, but because we're shifted over at 3, 1, 2, 3, my absolute value looks like this and like this. And they want to know the area under the curve between 1 and 4. So they want to know the area between 1 and let's say 4 is over here. So they want to know this area and this area. So how do I find it? Well, we can actually break up this integral into two different functions, because this one here is going to be negative x minus 3, and this one's going to be positive x plus 3. And so what you're going to want to do is break up the graph when this part here, let me get a different color. So this one over here is negative x minus 3. And this one over here is positive x minus 3. And so this part here is from 1 to 3, and this one's from 3 to 4. And so what you're going to do is you're going to rewrite this integral as two different integrals. So instead of writing the absolute value of dx, you're actually going to do negative x minus 3 dx. And that's going to be from 1 to 3 plus the area from 3 to 4 of x minus 3 dx. So basically all we're doing is we're summing this area here, and this area here depends on the line negative x plus 3, and this one here depends on the line x plus 3. So we're adding this area plus this area. And this area here corresponds to this piece of my integral. And this piece here corresponds to this area right over here. So we're just summing them up. So this is a trick to doing absolute value graphs, is to break them up into their respective piecewise functions. Okay. And so now what we're going to do from here is now we could evaluate this. And so let's go ahead and simplify. This is going to be the integral of 1 over 3 minus x plus 3 dx plus the integral from 3 to 4 of x minus 3 dx. And now we can integrate each one. And so if I integrate this term here, I'm going to get negative x squared over 2 plus 3. Actually, let's do different colors so that you can see which one I'm doing. I'm going to make this one over here pink. Actually, let's keep it consistent to what I wrote over there. So this one's going to be red. This is going to be negative x squared over 2 plus 3x. And then we're going to evaluate from 1 to 3. So I haven't evaluated yet, but I know I'm going to. So I'm going to keep those evaluation bars there. This means that we're going to evaluate. And I get rid of that integral or that funny little s because I already took that antiderivative. So I no longer need it. And then we're going to go ahead and add this integral here that has to do with this area over here. So if we add this, if we take the antiderivative of this, we're going to get x squared over 2 minus 3x, and we need to evaluate from 3 to 4. Now I'm going to copy and paste this over to the next page so that we have room. And okay. And so now we have to evaluate this. And so remember that in order to evaluate a definite integral, we do f of b minus f of a. So we do, let's go back to our notes over here. We're going to be doing f of b minus f of a. So that's exactly what we're going to do. So here we need to do, this is our f, we need to do f of b. So we're going to plug in b and then subtract our 1. And then plus the same thing over here. Plug in our 4 and then plug in our 3. So let me keep them in color so that you know what's going on. So this is going to be negative. So we know we're going to need to do f of 3 minus f of 1. And then we're going to do f plus f of 4 minus f of 3. So now you don't need to actually write that little step that I just wrote down there. This is for you to see what I'm plugging into that function. And so if we keep going and I plug this in, I'm going to get negative 3 all squared over 2 plus 3 times 3 minus, and then I highly recommend doing parentheses here when you're doing the minus. It's going to be minus my 1 into that function. It's going to be negative 1 squared over 2 plus 3 times 1. And now I'm going to add the next thing over, which is over here. This is going to be 4 squared over 2 minus 3 times 4 minus, and then big old parentheses over here so that I remember that I need to distribute that negative value. This is going to be minus 3 squared over 2 minus 3 times 3. Okay, perfect. So this is the same thing as negative 9 over 2 plus 9 minus negative 1/2 plus 3, and then plus 16 over 2, and I know I can simplify that, minus 12 minus 9 over 2 minus 9. Okay, and if we go ahead and simplify that, add them all together, this gives us just the answer 5 over 2. Okay, so I did this a little ahead of time, but now you know how to do it. So whenever you have the situation, remember, when you have a definite integral, you will do f of b minus f of a. So we're doing that evaluation theorem. And the trick to doing an absolute value function is to break it up into its piecewise function. Or if it helps to draw the graph so that you can see which one is going to be defined for what piece and which one's going to be defined for the other one. But you're welcome to also do just write that piecewise function and value. You don't have to graph it each time. And so after this, I'm going to stop this video now, and we'll go over to the next net change theorem in the next video. So hopefully we have a little bit shorter videos. I know I've been making them a little bit long, and I'm sorry, but I just kind of get excited and just go with it. And also I noticed that when I make shorter videos, Zoom gets them back to me a little bit faster. So I'm hoping this makes everything a little bit faster, because when they're really long, sometimes they take like up to a day for them to get sent to my email, and then I get annoyed because I'm like, oh, I want to upload it, and then yeah. So next thing we're going to talk about is the net change theorem, and that's the last thing in 5.3, and then we'll move on to 5.4.